let's see. Is there anything that you guys need to be made aware of? Gosh. Bear with me, guys. My cat is just being very rambunctious right now. What you guys should see in Canvas when you log in, just to jump in really quick to show you there. What we're covering today is factoring polynomials, which is section P4. So if you need to reference that in the textbook and the ebook, then you will look at the prerequisite chapter, section P4. Okay, so I was looking over that material earlier today, earlier this morning, and I sort of found the order in which it covered the topics of factorization a little bit convoluted. Now, what I mean by that is that I just didn't like the sequence in which it attacked the topic. So I'm going to attack the topic in a slightly different way. At the top of this lecture, we're going to really talk about factoring polynomials by examining their greatest common factors. So that's going to be one of our techniques. We're going to look at factoring by grouping, which is usually only used on polynomials that have 4 terms. And then we'll move on to factoring trinomials, which are polynomials with only 3 terms. We'll see how that's related to factoring by grouping. And then we'll look at some special cases of factorization. Okay. So let's dive in. Okay. Factoring polynomials. Okay, and again, this is section P4 in the ebook. Okay, well, last time we talked a lot about multiplying polynomials, and it turns out that factorization is sort of like dividing polynomials in some sense. Really, we're going to look at each of the terms in the polynomial expression and then see what each of the terms has in common. That's going to be the simplest way that we can begin factoring polynomials. But factoring, just to give you some vocabulary, is the process of writing an expression, so some algebraic expression, a polynomial or a set of numbers, as a product. Okay, so in that sense, I mean, like, let's look at a really concrete example with just numbers. So imagine that I gave you the numbers 12 plus 15. Okay, and we want to write this not as an addition problem or a statement of adding 2 numbers, but we want to write it as a multiplication problem, where we have something multiplied by maybe 2 other smaller, simpler numbers. Okay. Well, what we might do there is say, like, okay, if I look at 12 and 15, they are related in some sense, because I could look at the factors that multiply to make 12. In this case, you might say that this is 3 times 4. So we might write that as 3 times 4 here, just as a note to ourselves. And then we might write this as 3 times 5, since that is 15. Well, these numbers right here are some of the factors of 12 and 15. Okay. Well, if I wanted to sort of write this as a multiplication problem, you could think of this as reversing the distributive property. We can see that they have some common factor of 3, right? Each of them has a 3 sort of trapped inside of those numbers. Okay, so when we're going through this factoring process, what we're going to do is write this expression, this original expression that we have here, 12 plus 15, as a multiplication problem or as a product where we have something multiplied by something else. Okay, and usually that first thing that we're going to write is our GCF, which stands for the greatest common factor. That is the largest number that a set of terms has in common. The largest factor that a set of terms has in common. Okay, so if the greatest common factor for this set of terms is 3, then you can think about this as dividing 3 out of the original statement. So I'm going to write 3 right here because we want to multiply 3 times something to get our original expression back. Well, like I said, this is sort of like reversing the distributive property. So we might need 2 terms inside a set of parentheses here, such that when we multiply 3 by this term, we'll get 12 back. And when we multiply 3 by this term, we'll get 15 back. Well, if I take out the 3 from this first term, well, then there's going to be a 4 left over. And that makes sense because 3 times 4 will give us our 12 back. 3 times something will give us 15, and that something has to be this 5. So now I have this greatest common factor being multiplied by this set of terms. These 2 terms no longer have anything in common. So what we can say is that both of these factors multiply to make the original expression. And since for each of these terms, well, this is just one number, but for these 2 terms over here, they don't have any common factors any longer. So what we can say is that these 2 factors are prime and that this expression has been completely factored and written as a multiplication problem. Does that make sense? Or are there any questions?
No, I think you explained that really good.
Okay. Yeah, now I know that this example doesn't make too much sense. And what I mean by that is that if you were trying to simplify this expression with just numbers, it's just a purely numeric expression, you would just add the 2 numbers and then say that 12 plus 15 is 27. But with polynomials, we sort of have to think about it this way because we may have terms that are not like terms, so we won't be able to combine them. Okay, so let's sort of turn our attention to our first polynomial example, and then we will sort of examine what is the greatest common factor from a set of terms in a polynomial. Okay, so some polynomial examples. Let's just begin by identifying the GCF, or the greatest common factor. Okay, so let's look at the expression 6x to the 3rd power minus 4x. And we want to, again, write this as a product. So you can write an equal sign, or you could say that, write a little arrow here because we're trying to write this as something times something else. So if you need that little roadmap to just remind you, what is this process that we're doing? We're writing an expression that, it starts off looking like a subtraction, a statement of subtraction. We have this monomial being, and we're subtracting this other monomial. But can we write that as a product, something multiplied by something else? Okay. So when we identify the GCF, we need to look at these 2 terms and ask ourselves, what are all the factors of each of the terms? And what is the largest factor that can be identified in each of the terms that they have in common? Okay, so can anybody tell me what the greatest common factor is just by looking at these 2 terms?
2x.
2x. Does anybody have any ideas? Is it pretty obvious to everybody, or is it, let me ask it this way, because I want to make sure that there's nobody left behind here. Is there anyone who doesn't understand why 2x would be the greatest common factor here? Okay. Well, the reason is because we can look at this first term, and if we wanted to do some little scratch work, we could say that 6 is 2 times 3, and x to the third power is x times x times x. So we sort of examine the factors, break up that term, and look at what all is going on there. We can also break up this term here, which is negative 4x, as 2 times 2 times x. And then by sort of breaking that stuff up, we can see what do they have in common. It looks like we have a 2 in common here, and we have an x in common here. We have a 2 here and an x here, but that's the most that they have in common, the 2x. So 2x has to be our greatest common factor. We're going to write that term first, 2x, and we're going to multiply that by basically whatever we have left over. So I'm going to put a parentheses here to indicate multiplication. And then 2x times something should give me this original term back. Well, that something is going to be 3x squared, since there are 2 x's here. So 3x squared. And then finally, there's only a 2 left over here. Be careful, there's a minus sign here, so we need to put minus 2. And this should make sense. So we identify that this is our GCF. But the full factorization of this polynomial is 2x times 3x squared minus 2. The nice thing about factoring is that you can always check yourself. That is, we can check to see if our factorization is correct by just running through that multiplication in the forward direction. We might think of it that way. So last time we looked at multiplying polynomials, and we looked at some of that in our homework. Well, if I take this term here and multiply it back in to this set of parentheses, to these two terms, I should be getting 6x to the third minus 4x. And since that's the same as the original problem, that means that I have factored correctly. These are the correct factors. So correctly factored. Does anybody have any questions, comments, or concerns about that one? Okay. Let me maybe give you a couple more and sort of let you have at it. So 2. We'll look at negative 4x to the second power plus 12x minus 16. And then 3, we'll look at something a little bit more challenging, x minus 2 times 2x plus x minus 2 times 3. Okay. So really what I want you to be able to do right now is just identify what the greatest common factor is. And if you can, go ahead and factor these polynomials completely. And again, we're just factoring out the greatest common factor. I'll give you guys about 2 to 3 minutes to examine these. And when you're done, just type them in the chat and we'll discuss them here a bit. Does anybody have any questions? Or is anybody just completely stuck and not know where to start or even what I'm asking?
I'm understanding the second problem, but not really the third one.
Okay, yeah. Well, let's talk about the second one because it looks like we have somebody put the factorization, they put it in the chat, but we want to be careful when there's a negative number or a negative term for the first term. Okay, so typically, just as convention, in other words, just out of tradition, what we do when we have a negative first term is we tend to factor out the negative version of the greatest common factor. So what we should be doing is looking at these three terms and then assessing, what are their factors. We have a -1 times 2 times 2 times x for that first term. 12 can be broken down into 2 times 2 times 3 times x. That will give us our 12x. And then 16 is 4 times 4. But really, this is -1 times 2 times 2 times 2 times 2, which is 4 times 4. And I'm breaking them down completely into their prime factors. That is, 4 can be broken down into 2 times 2. And so we want to break down everything into its prime factors. And then we'll compare what are the prime factors that we have left over. And if we examine these terms, really, let's look at what do we have in common here? Well, people are saying 4 and -4. So that means that if we look at the terms, this one doesn't have an x, but it looks like they all are multiples of 4. And yeah, that looks right to me. This one has a 3, but none of the other ones have a 3. These two have x's, but the last one doesn't have an x. They all have to have that same factor in common in order for us to consider it the greatest common factor. So right now it just looks like it's 4, since 2 times 2 is a common set of factors that go into each of the terms. But because this first term is negative, what we're going to do is factor out the negative greatest common factor. So the GCF is usually written first, and we'll write -4, and we're going to multiply that by whatever's left over. So if I took out a -1, that means that I've used this factor here, right? So that means all I need is an x squared here. So this should make sense. -4 times x squared gives you -4x squared. If we're moving on to the next term, we want to think about -4 times 3x. Does that give us positive 12x? Well, it doesn't. So we have to sort of make a modification here. We have to say a negative times a negative will give us back this positive. So I'm going to put a minus 3x in the middle. And then again, we have a -4 times something to give us -16. Well, that has to be a positive 4. And again, we have the 2's here. That makes sense for the 4. And we have this -1 left over. But we already have a negative out here to multiply. So we've already used this -1. So you don't have to worry about that. The idea here is that you should just make sure that whatever this term is on the outside, the GCF, because this is a negative first term, we're going to pull out the negative GCF. But when we multiply that back in, we need to get the original term back. So we'll have to flip the signs in some cases in order to make sure that our signs are correct when we run through that multiplication. So -4 times x squared is -4x squared. -4 times -3x, and negative times negative should give us this positive 12x. -4 times a positive 4 gives us our -16. So this is the correct factorization. Okay. Now, I'm looking at this factor here, this polynomial factor. It's a trinomial because there are 3 terms. And to me, it looks like it can be factored further, but I really want to just practice on factoring out the GCF. So I'm going to leave this as it is. If you can identify that this thing can be factored further, that means that you're ahead of the game, that you remember something from a previous math class that will help you as we progress through the section. But we're going to leave it alone for now.
So why couldn't you just factor out 4 by itself?
It's not that you couldn't factor out 4 by itself, it's that by convention, that is by tradition, if the first term is negative, you will factor out a negative GCF.
Okay.
Okay, that is just the convention, the rule that we are going to use in this class.
All right.
But like if we were in the streets factoring polynomials as one does, I wouldn't care. But for this class, we're just going to be consistent. And if that first term is negative, you're going to factor out a negative GCF.
All right, thanks.
Yeah, you got it. Okay, so now looking at the second term, was anybody able to figure out how to factorize this and write it in terms of a product? It's a little bit strange.
I tried just adding it all or just doing the math. So I just did the multiplied 2x. I just multiplied the 2 sides and then I added them. And then I don't think I could factor after that.
Okay, so what I would say here is that if we are trying to factor that second problem, that is, we're trying to write this as a product and not as a sum or as an addition statement, then we should not be multiplying anything out, even though it's going to be our first sort of instinct to go ahead and sort of distribute this out, distribute that out, combine like terms. So you need to like not be on autopilot when we're thinking about factoring. You need to be thinking about what are the common factors for one term, for each of the terms in your polynomial. So can anybody tell me how many terms are in this expression here? I see in the chat, somebody said 4. And that's a good guess. Does anybody have any other good guesses?
3.
Why 3?
The 2x, I mean the x minus 2, there's 2 of them.
Oh, I see what you're saying. Yeah, because you're saying that x minus 2 is its term, 2x is a separate term, and then 3 is a separate term.
Yes.
Like they're distinct terms. Okay, I gotcha. Does anybody remember what a term is? Okay, so a term is a number or monomial that is added or subtracted with other numbers or monomials. And I guess I could have cut down the writing there. A number is a monomial. So the idea here behind a term, or what I'm trying to get you to identify, is that if you are adding or subtracting things, actually, this should be a polynomial, not a monomial. What we should be focused on here is the addition symbol here. The addition symbol here is separating our 2 terms. So when you look at this thing, you should say, this is a term and this is a term. Okay. Now I can imagine students being confused when I say that, because there's a subtraction symbol here, And x minus 2, well, that's a monomial and you're subtracting a number. But if you sort of zoom out a little bit, you see that this is really a binomial being multiplied by a monomial. And this is a binomial being multiplied by a monomial as well. So if we're multiplying within this set of terms, or within this set of objects, then we can't call these terms, because we're multiplying the things that you multiply together we call factors. So we have a binomial factor here, x minus 2, and a monomial factor here. That's our first term. Then for our second term, we have a binomial factor and a numeric or a monomial factor. So if I'm comparing the two terms and I'm asking you, what is their greatest common factor? Well, they both have this same binomial factor in common. So they have the same binomial factor. So the GCF, or the greatest common factor, in this case is not a single number. It's a polynomial, which is x minus 2. So if I want to write this as a product, I'm going to write it as the GCF times whatever's left over when I factor that thing out. So what I can do is, set up these little space holders like I like to set up, something times something else. And the GCF is usually what we write first. And the GCF in this case is this binomial x minus 2. That is being multiplied by something else, which should give us two terms. And if we factored out the x minus 2 here, what would be left over is 2x. Plus, we factor out the x minus 2, so what's left over here is the 3. So you can think about it like if we wanted to check ourselves on this one, and maybe I should move to another sheet of paper. We have x minus 2 times 2x minus 3, right? Or is it plus 3? We want to check ourselves. Then we can take and use the distributive property the way we would with just a single number, but this time we're going to use a binomial factor to multiply it into the second set of parentheses. So think of this as one large thing, and we're going to multiply it into the parentheses, so to speak, such that we would write this as x minus 2 times 2x. And you could also do that same thing here. Pretend that this whole chunk of stuff is a number, and we're going to multiply it by the 3. So you would write plus x minus 2 times 3. And that's the original problem. So that means that this is the correct factorization. We have a set of two terms over here inside this parentheses. We have a binomial times another binomial. And those are the factors that when you multiply them out, you get this. Now, can you multiply further and then combine like terms and then get a long string of a polynomial? Maybe it's a 4-term problem or a 3-term problem. Yes, but we're writing this as a product such that the polynomials that we're multiplying are both prime. That is, they can no longer be factored. So this is the correct factorization. Run out of space. And we'll take a look at another example that's similar to that. So let me give you guys some problems to practice, and I'm going to throw you guys into a breakout room so that you can work amongst yourselves and see if we can sort of tackle those problems. So practice. And we want to factor out the GCF. Okay. 9y to the 5th plus y squared to 6x squared t plus 8xt minus 12t, and then the challenging ones. 14 m plus 1 quantity cubed minus 28 m plus 1 quantity squared minus 7 m plus 1. And I'll give you one more just for good measure. 24 x minus 2 cubed minus 16 x minus 2 squared plus 6 times x minus 2. Okay, so write this down, and I'm going to open up the breakout rooms. Once you get that invitation, go ahead and join the breakout room, and then we're going to spend about 5 to 10 minutes working those out, talking amongst yourselves and asking questions to try to figure out how do we factor these things. The first two seem pretty straightforward, but the last two may be a little bit more challenging. So. Okay, the breakout rooms are now open, so make sure that once you write this down, you go ahead and jump into those breakout rooms. Okay, I think that everybody is sort of waiting to be admitted back to the main session, but I wanted to go ahead and start this thing off. I think that the first problem was probably the most straightforward one. Obviously, that's sort of, I was intending to ramp them up in terms of difficulty as they progressed. But for this first factorization, I'm going to sort of gloss over the details here. The two terms have a y in common. So I'm going to write this as y times 9y to the 4th power plus, oh, this was a y squared, wasn't it? Plus, oh, I've already factored this incorrectly. Let me go ahead and back up since I wrote the problem down wrong. So we had 9y to the 5th power plus y to the 2nd power, and we needed to factorize that. Well, these two terms have a y squared in common, so we're going to factor that out and then ask ourselves, y squared times what will give us 9y to the 5th power? Well, that has to be 9y to the 3rd power, so that we multiply those y's back together and we have a sequence of multiplying y times y times y times y times y, so that's y to the 5th. And then y squared times something needs to give me y squared back. So what should that something be?
One.
It should be 1. It should be a positive 1. So a lot of times students will factor out the y squared and then they'll say, well, I've already taken out the y squared. There shouldn't be anything here. But again, we're thinking about multiplying to get the original terms back. So if you didn't put anything there, then there would be nothing to multiply. So you wouldn't be able to get this term back. We have to think about y squared times 1 giving itself back. Okay, so this is the correct factorization. For the second problem, we had a trinomial, so 3 terms, 6x squared t plus 8x t minus 12t, and we sort of wanted to write that as a product. And the first thing I might do is look at these terms and then examine that they all have a 2 in common at the very least. They don't all have x's, but they also all have t's. So I sort of go through each of the terms, the numeric, and then each of the variable terms or factors. And the GCF in this case is going to be 2t, since all of them have a factor of 2t. So then I'll open up my parentheses, and I'm thinking about this like there are three things that I need to put in here so that when I multiply 2t times this set of terms in the parentheses, that I'll get the three terms that I had back. Okay. So in that case, 2t times 3, I need an x squared in order to get 6x squared t back. This is a positive term, so I'm going to put a plus here. 2t times 4x should give me my 8xt back. And then finally, 2t times, well, this has to be a negative 6 to give me my negative 12t back. And so this whole thing is completely factored. You have this monomial factor here, the 2t. And then you have this trinomial factor. And one way that you can sort of tell that it's fully factored is that if we look at this trinomial, the 3x squared, the 4x, and the 6, they don't all have some common factor among them. So the 3 and the 6 maybe do, and the 4 and the 6 do, but they all have to have that common factor if we're going to continue that factorization process. So we have to stop.
Sorry, I have a question.
Yeah.
Since the 3x squared plus 4x minus 6 is a quadratic equation, would we still factor that?
So I'm going to be a little bit nitpicky here. It's not a quadratic equation, but it is a quadratic trinomial expression. Equations have equal signs. And so I want to make that clear, because when we solve equations that look really similar, like quadratic polynomials look similar to quadratic equations, but they're not the same kind of thing. You don't approach them the same way. So that's the only reason I'm being that nitpicky. But it is a quadratic polynomial or trinomial. But what I'm saying is that this may be factorable here, but this first part of the class, we're just factoring out the GCF. That's all we're doing. Those are the instructions that I gave you. So we're not going to do anything more than factoring out the GCF.
Okay.
We'll get to factoring trinomials here in a bit. Okay. And just for the interest of time, I'm going to only solve one of these last two problems, or only factor one of them. So let's look at the first one. 3, I gave you 14 m plus 1 to the third power minus 28 m plus 1 to the second power minus 7 m plus 1. Okay. So here I need to be thinking about, I have this term, and this term. Within the terms, they're made up of factors or numbers that are being multiplied by each other. So this is like 14 times this polynomial, m plus 1. And really there are 3 factors of that, since it's being multiplied by itself 3 times based on that exponent. This is negative 28 times m plus 1, the binomial, raised to the second power. So there's a factor of 28 here, there's a factor of m plus 1, and that has 2 copies. Then we have a factor of 7 times a factor of m plus 1. But we're trying to identify the greatest common factor. So you can think about writing this as, this first term, if you really wanted to break it down all the way, 2 times 7 would give us the 14. And then you have a factor of m plus 1, m plus 1, and m plus 1 all being multiplied by each other. All of that is the first term. The second term you could think of as being 2 times 7 would give us 14, but we need another 2 to get us to 28. And then you have m plus 1 and m plus 1. And then all we have here is 7, which is prime, and m plus 1. I'm sort of being very hand wavy with the negative signs. I'm not really focused on them, but they may be important later. We'll see. But I'm looking at these sets of terms that have sort of broken down into all of their factors. I've completely factored each of the terms. And I want to explore what do they have in common. Well, each of them has a 7. Not all of them has a 2. And then each of them has this binomial factor of m plus 1. So what that signals to me is that the GCF here should be 7 times m plus 1. That's my GCF. And so the process is going to be no different from when we factored out a single monomial. I'm going to write the GCF first. There's my GCF, which in this case is 7 times m plus 1. And that needs to be multiplied by something so that I get these 3 original terms back. So you can think of it as I need 3 boxes in here. And we'll see what we have left over when we factor out the GCF. So for the first term, I got rid of the 7, or I took that out, and I took out one of these factors of m plus 1. So that means what I have left over is 2 times m plus 1 squared. And I know that parentheses on parentheses looks really confusing, but just go with me here. This is what is left over. So we're just going to go ahead and write that in because the process should be the same, right? Again, the idea in mathematics and algebra is that the processes remain the same, even though the problems change or look a little bit funny. So as long as you're carrying out the same process, you should be okay. The second term, what we have left over is 4, which should be negative, and m plus 1. Right? 2 times 2 is 4, and we have an m plus 1 left over. Then over here, we took out the 7, and we took out the m plus 1. So that means what we should have left over, since this is a negative symbol, something times itself gives itself, something times 1 should give it the original statement back. So that should be a 1, a negative 1. Does that make sense? So just think about running this multiplication forward. If I multiplied this GCF by the first term in the parentheses, I would have 14, and then m plus 1 times m plus 1 squared should be m plus 1 to the 3rd power. This GCF times the second term would give me a negative 28, and then m plus 1 times itself should give me m plus 1 squared. Finally, this thing times a negative 1 should be the negative version of itself. You guys okay with that? Maybe not okay with it, but is that sort of clear? Yeah. So you might be thinking like, okay, what do I do with the rest of this stuff? Because having all of these terms in the parentheses is a little bit confusing. Well, what you would do in this case is you would go ahead and take this second set of parentheses and multiply everything out. So I'm not going to bore you with the details here. The idea here is that you could simplify this further by distributing or multiplying this out so that you got some weird stuff. So let me just go ahead and run through it really quickly. The main idea, though, is that we needed to factor out this GCF. So this would have been 2 times m plus 1 times itself would be m squared plus 2m plus 1. This, if we multiplied this out, would be negative 4m minus 4, and then that's just a minus 1 over there. So we still have the GCF out here. Okay, but we're going to go ahead and simplify everything that's in this set of parentheses. I've changed them into brackets just so that we can clearly sort of segregate it from the the GCF, which we've already done so much work to pull out. We're going to go ahead and distribute this out so that what we have left over here is 2m squared plus 4m plus 2. Then we have minus 4m minus 4 from that first round of distributing, minus 1. And now we just need to clean up the stuff that's inside of what I've written in brackets. And we'll have 7m plus 1. And I'm going to change the brackets back to parentheses because when we go ahead and combine like terms here, we have m's, looks like those cancel out since they're the opposite sign. So we should have 2m squared, and then this should be -2, -3. And so now we have a statement here at the end where you have a number times a binomial factor times another binomial factor. So we can say that this is fully factored now. Okay. But I'm sort of going to leave that last one for us as a challenge. So what I recommend to you is to look at this, these sets of notes and then try to apply it to that fourth problem, because we just, in the interest of time, need to move on to the next factoring technique. Okay. Okay. Factoring by grouping. Factoring by grouping is usually how we will factor 4-term polynomials. So that first technique, factoring out the GCF, can be done on any kind of polynomial, regardless of how many terms there are. So there could be 2, 3, 4, 5, and so on. As long as each of the terms has something in common, you will be able to factor out the greatest common factor. But in some of these cases, we'll look at these 4-term polynomials where maybe only 2 terms have a common factor and then the other 2 terms have some common factor. And we won't be able to just simply factor out a common factor from each of the 4 terms. So let's first look at, let's examine x to the third minus 2x squared minus 3x plus 6. Okay. Does anybody know how they would go about factoring this? What do you think the first step would be?
There's 4 terms, so you would group 2 terms together.
Yeah. Yeah, so what do you mean by 2 terms together?
Like taking 2 of your terms and like the x cubed minus the 2x squared and grouping that.
Yes, grouping. These are good terms to be using. So in math, in algebra, when we're talking about polynomials or real numbers, there's this idea that when you add or subtract certain things, that you can group the numbers together in whatever groupings you want. And you should get the same result when you run through the addition or the subtraction. So what I mean by that in sort of a concrete example, is that we have this associative property. So let me just stick with purely numerical expressions. If I had 2 plus 3 plus 7 minus 4, I could group these terms together however I saw fit. So I could put 2 plus 3 and then do that first. I could do the 7 minus 4 next, and then go ahead and resolve the problem. Or if I wanted to, 2 plus 3 plus 7 minus 4, same order hasn't changed. But if I wanted to group these where I had the 3 plus the 7, I could throw parentheses on there, group the 3 plus the 7, do that first, get the 10, and I'm still going to get the same result when I simplify the expression. So this grouping property is going to be super useful because if you look at these 4 terms, they don't all have some common factor. Maybe these 2 do, and maybe these 2 do, right? So what we can say then is that let's group these terms together, x to the 3rd minus 2x squared minus 3x plus 6. And maybe first I'm going to put a little plus sign here, because when you add a negative 3x, that's the same as just simply subtracting. But I'm going to throw parentheses around the first 2 terms, and then throw parentheses around the second 2 terms. And then I'm going to treat them separately. I'm going to say, if I was looking at this as though it's a polynomial that I wanted to factor, because they have some common factor, can I just factor out the GCF from these 2 terms? Well, sure. Let's take a look at these. What is the GCF if I'm looking at these 2 terms?
X squared.
X squared. So if I was pretending that was my problem, x cubed minus 2x squared, and I just wanted to factor out their greatest common factor. Again, I'm sort of putting my hand over this other thing. We're going to hold that to the side. What I would write is x squared times x minus 2. And that would return to me this original expression here. Does anybody have any questions about that part? Okay, so once you factor out the GCF from the first 2 terms, we're going to ignore the first 2 terms and focus on the last 2 terms. Looks like we have another binomial where the 2 terms have a common factor. The common factor in this case looks like it's a 3, but since that first term is negative, we're going to factor out a negative 3. So I'm going to write minus 3 times x minus 2. Does anybody have any questions about this minus sign? Or about what I just did here in general? So since we're treating this as its own sort of smaller polynomial from which we're factoring out the greatest common factor, negative 3 times x should give us our negative 3x back. And negative 3 times negative 2 should give us the positive 6 back. So that is the correct factorization there. But now when we look at the entire expression, we have this term here and this term here, and they both have some common factor. They have a common binomial factor. That is this stuff, x minus 2 is common between the 2 terms. So that means we can factor out the greatest common factor once again. So we can pull this x minus 2 out and call that our greatest common factor. And I'm just going to use the colors to emphasize here. That's our GCF. And then we're going to multiply that by whatever's left over. Well, the stuff that was left over, if we took this out, is x squared minus 3. And sure enough, if we run through that multiplication, and then sort of distribute this out again, we'll get our original statement back. But I'll leave the checking for you guys. Does anybody have any questions about that?
Yeah, I do.
What's your question?
At what point would you take away the addition sign in between the 2 terms? Yeah. that one.
Well, you just have to realize that when you're subtracting, that's the same thing as adding a negative, right? The only reason I put the addition sign here is so that I can group these 2 terms together and group these 2 terms together. You don't have to put the plus sign there. It's sort of like a visual trick. But that would be the same. That would be the same thing as if I had these numbers over here, right? 2 plus 3 plus 7 plus negative 4 is the exact same thing as just saying subtract 4.
Okay.
Yeah. But typically the associative property is shown where there's like a plus sign in between the two groups. So that's the only reason why I threw the plus sign in there.
All right, thanks.
So there's our factorization. So let me give you guys some practice problems, and we won't utilize the breakout rooms, but I'll give you guys a moment to sort of solve these. So the first one I want you guys to attack is x cubed plus x squared minus 5x minus 5. Go ahead and factor that one. And let me grab another practice problem for you guys. Maybe something that's a little bit more challenging. 2y squared plus az minus 2z minus ay squared. And I'll give you guys about 5 minutes to try to factor these out, factor by grouping. And when you're done factoring these by grouping, you can go ahead and throw a thumbs up in the chat or use the thumbs up reaction in Zoom. Does anybody have any questions? Is anybody just like completely stuck?
Yeah, number 2.
And what seems to be the problem that's like holding you up on number 2?
I don't see any I don't see, when I'm grouping them, I don't see anything that any of the terms have in common or any of the numbers have in common.
Well, how are you grouping them?
So I'm grouping 2y squared plus az
Yeah.
and negative 2z minus ay squared.
Oh, I can see your issue. Because these two terms don't have anything in common, right?
Oh,
And
okay,
then
yeah, now I
these
see
two
it.
terms don't
I
have
see
anything
it
in
now.
common, right?
Yeah, I see it now.
Yeah.
Yeah.
So the trick is that you're not going to be able to, for every case, just throw parentheses on the first two terms and the second two terms. You may have to rearrange the polynomial a bit so that you can group together two terms that have something in common. So that was the trick there. And I'm glad you brought that up. Very good question. What I would do is rewrite this as 2y squared minus ay squared, taking care of the first two, the outer terms here. And then I would say plus az minus 2z. And then I would go ahead and group these together. Because now the first two terms, as I've rearranged them, do have a common factor. And the second two terms, again, as I've rearranged them, do have a common factor. So you may have to do a little bit more processing than just throwing some parentheses on.
But then again, looking at the way you factored it,
Mhm.
it should be shouldn't it be a negative? Okay, no, never mind. I was looking at the wrong thing. Never mind. Thanks.
Well, I definitely think that the order in which I did some things might need to be rearranged at some later point, but we should be getting the same thing. So just keep working on that. I think I'm going to go ahead and jump in and factor the first one, though. I think that this one was definitely more straightforward because it's pretty apparent that these two terms and then the latter two terms have something in common. Oh, and then for whomever it was that asked about that addition symbol, the reason why I put it is because if I just throw parentheses on these two terms and parentheses on these two terms, it looks sort of like I'm multiplying a binomial times a binomial. But I need to be very clear that I'm not, this is like the sum of terms. It's not a product. So that's why I just put a little plus symbol in between to say, just to remind myself again, I didn't multiply. The original problem didn't say to multiply anything together. It was originally a statement of addition and subtraction. So, but then for the first two terms, these guys have something in common, which is the x squared. So I should have x plus 1 left over there. These guys have a -5 in common, so I'm going to factor that out, x plus 1 as well. You see that the x plus 1 among these two terms, that factor is common. So we should be finishing up with x plus 1 times x squared minus 5. And that is the final factorization for that problem. Now, one question that I get a lot from students each semester is that, does it matter what order in which I put these two polynomials? And the answer to that question is no, because if you're multiplying x plus 1 times x squared minus 5, if you just switch the order there and wrote x squared minus 5 times x plus 1, that shouldn't change anything. The order of multiplication doesn't matter, in the same way that 2 times 3 is still equal to 6. And then when I flip that order, 3 times 2, you still get 6. With polynomial multiplication, the same thing is true. The order doesn't matter. So if you wrote this as your answer, that would be accepted as Cengage WebAssign would accept that as your answer. If you wrote this as your answer, it would be accepted as well, provided that you correctly factored the problem. Okay. Now for the second problem, let's go ahead and just run through it. These two terms look like they have a y squared in common. That's their greatest common factor. So now I have a 2 minus a here. Over here, we have a z in common. So we have a positive z in common. And we have an a minus 2 here. And something looks wrong. Because this factor 2 minus a is not the same thing as a minus 2. So maybe I've rearranged or ordered this problem incorrectly. Maybe I want to group them differently. There is a fancy trick that you can do to sort of change the order of some of these things. For instance, if I factored out a -1 here, which you can do, let's say that I factor out a -z instead. Well, if I factor out a -z instead, then I would have a -a to give me that positive az, and then -z times, this would have to be a +2 to give me the -2z back. Well, already it seems really convoluted, but let's go ahead and go with it. We have 2 minus a over here, -z, and then we have a -a plus 2. Still looks different from this factor over here. But within this factor, we're just adding terms. So when it comes to addition, you can switch the order and it won't make a difference. So we could write this as 2 minus a, and that's the same thing as -a plus 2. So if we did that, sure enough, we could get these two factors to match. And that's sort of what we're looking for, the 2a and the 2 minus a rather, to match, so that we can say that's the greatest common factor. Let's go ahead and take 2 minus a out. And then we have our y squared minus z left over. And that completes the factorization. But I'm sure that these steps right here seem really weird. And maybe none of that seemed natural to you at all, or none of it felt good. So what I'm going to suggest is that when those terms in the original polynomial are out of order, what you want to do is swap the second and the fourth term. Okay, I think that what I had done originally was I just moved the fourth term into the second position, and then I just sort of scooted everything back. Okay, but let's go ahead and do that again, where I just swapped the positions of the second and the fourth term. So we had 2y squared plus az minus 2z minus ay squared. And this time, again, instead of moving this to the second position and scooting everything back, we're going to take the second and the fourth term and then swap them entirely. So they're going to switch positions. But the first and the third term will stay in the same position. So we'll have 2y squared. Then we have minus ay squared. That looks nice now because they have a y squared in common. But now I'm going to put -2z plus az. And now when we go ahead and group these things, we should see that we shouldn't run into any problems where we have to do any weird tricks where we factor out a -1. So this will have a y squared in common. We have a 2 minus a. That looks good. Over here, we have a first term, which is negative. So I'm going to factor out a -z. That will leave me with a 2. If I factor out a -z, then I need another negative to give me this positive az. And that just straight away, we have the same factor among those two terms. So since those match, we can proceed by pulling out the greatest common factor, which is 2 minus a. And then our remaining factor is 2y minus, y squared minus z. And that was a lot cleaner with less sort of algebraic acrobatics than the previous attempt. Okay, so some orderings will be easier, and you may have to, run through the problem, reorder it. If it gets more complicated than you're able to deal with, just start back at the top, change the ordering. But my trick there is just swapping the second and the fourth term seems, for whatever reason, to be the trick that will help you factor by group. Okay. So we're going to move on to the next method for factorization, and that is factoring trinomials using what I call the AC method. Okay. And the reason why we sort of didn't have that many practice problems for factoring by grouping is because you will see that when we get into the process of factoring using the AC method, that the factoring by grouping algorithm will sort of rear its ugly head. So we're going to factor trinomials. So these are 3-term problems using the AC method. In the textbook, they talk about the FOIL method. I find that method to be more confusing for students. And the AC method is really a method for taking a 3-term problem, breaking up the middle term, and then turning it into a 4-term problem so that you can just fall back on factoring by grouping. So the AC method turns our 3-term problem back into a 4-term problem. Okay, so let me grab an example of a trinomial that we're going to need to be able to factor. So here's going to be our first example. 4y squared minus 11y plus 6. Okay. Well, right away, if we examine each of the terms in this polynomial expression, there are 3 terms, 1, 2, 3. You might call this a quadratic trinomial because we have a term that's squared, but again, we're going to talk about equations later. So we might not refer to this as a quadratic yet, just as a trinomial. We want to write this as a product, that is some polynomial times another polynomial. Right now it's written as a sum, right? We have some subtracted terms and some added terms. You might try to attack this by seeing what all the terms have in common, what is their greatest common factor. But when you look at each of them, that 11y is sort of messing up the greatest common factor algorithm. So we can't factor something out of each of them because that 11 is prime and has nothing in common with the 4 or with the 6. Okay. You might try factoring by grouping because the first terms have a y, but you need to group that in sets of 2. And so you would have this odd man out that you wouldn't be able to factor out. So what are we going to do here? Okay, well, this method, I will teach you the process for it. And the only reason we use it is because it works. Okay. You might ask, why am I doing this? Why am I about to multiply some of these numbers together? And I'm just going to tell you, because it works. Don't think any more deeply about it than that. So the first step in this process, in our AC method, is we're going to label our terms or really the coefficients, so the numbers in front of the terms. So we're going to say A is equal to 4, B is equal to negative 11, and C is equal to 6. The reason why this is called the AC method is because we're going to multiply A times C, and then we're going to examine the factors of that. So examine the factors of A times C. So in this case, we have 4 times 6. So let me go ahead and write this problem over here. We have 4y squared minus 11y plus 6. And this requires sort of a lot of scratch space. A times C in this case, 4 times 6 is 24. And we're going to examine the factors of 24 using a t-chart. So we want to list all of the numbers that multiply to make 24, every factor pair. So 1 times 24, 2 times 12, 3 times 8, 4 times 6, 5 doesn't work, and then we're back at 6. Okay. The next thing we want to do is select the pair of factors, or the factor pair, that combine to make whatever the number b is. So in our problem, in this particular one, b is -11. So I'm trying to get factors of 24 that will add or subtract and give us -11. Okay, so if I look at this factor pair and I want to select one of the factor pairs that will give us 11, well, it looks like 3 and 8 will give us 11. But the key thing here is that we need these factors to multiply to make 24, to make that a times c, and they need to add to make that -11. Well, the only way that 3 and 8 are going to give us -11 when you add them is that they would both have to be negative. And so both of these conditions must be met in order for us to say that this is the correct factor pair. -3 plus -8 will give us the -11, and that must mean that -3 times -8 should multiply to give us +24. And since that works, we need to say our factors that we're going to use here are -3 and -8. Okay. So then once we've done that process, we're going to go back to the original trinomial, the original set of 3 terms. We're going to take the middle term and do what Bernie Sanders wants to do and break up the big banks. And what I mean by that is we're going to take -11y and write it as negative. I'm going to write this as -8y minus 3y. Okay. These two numbers come from this factor pair that we selected. And I'm going to write the whole polynomial back down. So these two terms on the end, the 4y squared and the +6, can come down. And so now we have a 4-term problem, which is equal to our original 3-term problem, right? Because if I were to combine like terms, this -8y and the -3y would combine to make our -11y. So we haven't really changed the value of the problem. We've merely broken up the middle term in a convenient way such that now the first 2 terms have a common factor and the second 2 terms have a common factor. So we can just factor by grouping at this point. Okay, so now we can say, let's throw some parentheses on this problem. I'm going to put my little plus sign here just to be mathematically correct. And now we have these 2 terms. If we're trying to factor out their greatest common factor, looks like a 4 is common to both of them, and then a y. So 4y is the common factor there, and that would leave us with a y minus 2. For the second set of terms, we should have a -3 that's common among them. Then we'll sort of flip the sign, so we have y minus 2 there as well. Again, -3 times y will give us the -3y back, and then -3 times the -2 will give us a +6 back. If these factors here in the parentheses do not match, you've done something wrong. So that's a good self-check to make sure that you're on the right track. They need to match exactly. These 2 terms need to be the same with the same sign in between them. Okay, otherwise you've done something wrong or have to do some sort of finagling to try to make them look more similar. But since we're good here, we can say that y minus 2 is the greatest common factor, so we're going to factor that out. and then 4y minus 3 is the remaining factor, and we're done. That's the process. So the big sort of heavy lift of the AC method is figuring out, labeling the terms, multiplying A times C, trying to select the correct factors of whatever this number turns out to be, such that you can break up the middle term and then go right back into factoring by grouping. So I'm going to work one more example with you guys and then sort of give you one to work on your own. So let's do we have something more challenging? Yeah, let's do this one. 16y to the third plus 24y to the second minus 16y. Okay. So can anybody tell me what the first step in factoring this trinomial should be?
Label your terms.
Yeah, let's label the terms. Hold on.
Factor the y's.
Before we do that, we always want to inspect to see if there's a greatest common factor among the terms. So always, always, always check to see if there's some factor in common between all three terms. Always check for a GCF. And in this case, if we go ahead and factor out the GCF, we won't have to multiply 16 times 16 and then get some outrageously large number. Okay, because it looks like 16y to the third, 24y squared, negative 16y, they all have an 8 in common and they all have a y in common. So we could say that we have 8y times a set of 3 terms, and that would be 2y squared. This would be plus 3y. Yeah, and then this would be a minus 2. Okay, so we factor out the GCF first. And then to fully factorize everything, we need to make sure that we have this monomial factor, but we need to make sure that this trinomial factor can't be factored any further. So here is where we're going to apply the AC method. And because we factor out the 8y before, multiplying 2 times 2 is going to be so much easier, right? 2 times 2 is just 4. 16 times 16 is, only calculators know what that is. So we'll go ahead and now start with the AC method, label this as A, B, and C. Remember, the labels just go on the coefficients, not the variable parts. And then we'll do our scratch work. So A times C is equal to 2 times 2, which is 4. In this case, it's 2 times a negative 2, so really this is a negative 4. And then we'll look at the factors of negative 4, which are 1 and 4, 2 and 2, and I'm sort of playing it loose with the negative sign. We need to select the factor pair here that will meet these criteria, right? They need to multiply to give us our negative 4, and they need to add to give us B, which in this case is 3. Well, if I just straight up add 1 and 4, I will get 5. And if I add 2 and 2, I will get 4. So right off the bat, you might be stuck here until you remember that this is a negative number. So one of these factors has to be negative in order to multiply to make a negative, right? A negative times a positive gives you this negative. So we can sort of figure out which number we're going to make negative. And in this case, if we make it a -1 and a 4 and add those together, that will give us our 3. And then -1 times our 4 will give us our -4. So these are the factors that will satisfy the condition that we need. We can go back to this trinomial and take that middle term and break it up. And you can break it up however you see fit. You might put negative You don't have to put -1y. You can just put -y, and that's the same thing as -1y plus 4y. And then just realize that if you were to put those back together and combine like terms, you would get that middle term. So you haven't changed the value of the original trinomial. We'll bring down our 2y squared and our -2 on the end. And I'm sort of going to let the GCF hang out, but we can't forget about that later. We'll throw some parentheses on this so that we can factor by grouping. These two guys have a y in common. So we'll have 2y minus 1 there. Then over here, these guys have a 2 in common, so a +2. And we should have a 2y minus 1 there as well. Again, these factors here match. So that's our greatest common factor. We can finish the job, pull out our greatest common factor, and then our remaining factor is the y plus 2. But don't forget that we originally pulled out the GCF, so we have to multiply that into our final factorization. That 8y we can just stick right in the front, and that will be this. We have fully factored that problem. Okay, so with the last 5 minutes, let me give you guys one problem to work yourselves. So let's try this one. 24x squared plus 42x plus 15. Try to factor that one out. And when you're done, as always, you can just throw the thumbs up in the chat or use the thumbs up reaction in Zoom. Yeah, Tessa, it looks like you correctly identified that all of these three factors have, all of the three terms have a factor of 3 in common. But then that remaining trinomial that you have in parentheses, that should be factorable as well. So we need to completely factor that. So you need to continue using the AC method on that trinomial. But again, in the interest of time, I'll just go ahead and jump in and sort of start narrating this. So we correctly identified that each of these three terms has a 3 in common. That's our common factor. 3 times 8x squared plus, this is 6 times 7. So if I take out a 3, that'll be 2 times 7, that's 14. And then this should be a 5. So then we're going to apply the AC method. And then sometimes maybe in the past, you've seen this method of writing things down. It's the same thing. People do this X, they put A times C here. which would be 8 times 5, which is 40. And then we need to get b, which is 14. So the factors of 40, that will give me 14. And that should be 4 and 10. Okay. So that's if you didn't want to use a t-chart. I prefer to use the t-chart so that we can be thorough about exploring the factors 1 and 40, 2 and 20, 4 and 10, 5 and 8. And that's it. Okay. But we chose 4 and 10. So we're going to break up the middle term here into 4x plus 10x, and then bring down our 8x squared plus our 4x plus our 10x plus our 5. And then we can go ahead and factor by grouping here. So we have these two terms grouped together. We have a 4x in common over here. So that gives us 2x plus 1. Over here we have a 5 in common, so we'll pull out that 5, leaving us with 2x plus 1 here as well. The 2x plus 1 is common, so I'm going to pull that out finally, and then leave my 4x plus 5 as its own factor. But you absolutely cannot forget that we factored out the GCF at the very beginning. So our final answer should be 3 times 2x plus 1 times 4x plus 5. And that would be the full factorization. Okay. Now, we didn't have enough time to sort of get into the special factoring. There are some special factoring formulas. I will make a video on that and upload it to Canvas so that you can have it to use on the homework, but we'll also discuss that at the top of the class next time before we get into some more material. So if you have any questions or need to review this video, it will be posted to Canvas later. But that is the time we have. If you have questions, you're more than welcome to hang back and talk with me for a bit after this. But if you have no questions, you are free to go.
Have a good one.
You too.
Have a good